Okay, so we're going to be looking at redox reactions in fatty acid metabolism. So for this first problem, we're trying to make a 10-carbon fatty acyl derivative from 5 molecules of acetyl-CoA. So we can start by identifying our electron donors and our electron acceptor. And because this is a synthesis reaction, you know that your electron donor is going to be NADPH. And then your electron acceptor is just going to be acetyl-CoA. Okay, so we can start by writing the oxidation half reaction. So that will just be NADPH, which will eventually make NADP+. So again, it's a 10-carbon fatty acyl derivative, and you're making that from 5 molecules of acetyl-CoA. So that's your 5 molecules of acetyl-CoA, just like a simple diagram of it. So to be able to link all of these acetyl-CoA to make your 10-carbon fatty acid, it's going to take 4 rounds of synthesis. And then if we go over here, we can see that it takes 2 NADPHs to make per cycle of synthesis. So 1 round of synthesis equals to NADPH getting turned into 2 NADP+. And then with 5 molecules of acetyl-CoA being combined, it's going to take 4 rounds. So therefore, you're going to make 8 NADPH, or you're going to use 8 NADPH to make 8 NADP+. And then like all redox reactions, we need to balance this equation. So we can start by balancing the hydrogens. So over here we have 8 hydrogens, and then we don't have any on the right-hand side. So you can just add 8 hydrogens. And then now we can balance our charges. So we have the 8 from the NADP+, and then the 8 from the hydrogens. So now we have 16 positive charges on the right-hand side. So to balance that, we just add 16 electrons onto that. Okay, so that's done for the oxidation half reaction. So now we can just move on to the reduction half reaction. So with this, we start with 5 molecules of acetyl-CoA. And then that eventually gets turned into your 10-carbon fatty acyl derivative. And because this isn't a fatty acid yet, it's just a fatty acyl derivative, you're going to have your ACP, which is your acyl carrier protein. It's just going to be tagged onto the end of that. So now we can go ahead and balance out the atoms that we have. So first we see we have CoA over here, but it's not on the right-hand side. So we need to add it to that. So we have 5 molecules of CoA, so we'll add 5 CoA SH. That's being turned out from the other side of the reaction. And then over here we have our acyl carrier protein, but it's not accounted for on the left-hand side. So we can add our ACP SH. And we just need 1 of those. Okay, so now we can balance out our oxygens. So if you remember the structure of acetyl-CoA, it looks something like this. So we'll actually have 5 oxygens from our 5 acetyl-CoA. So 5 oxygens. And then on our right-hand side, we have this 1 oxygen over here. So in order to balance this out, we're going to need to add 4 waters onto the right-hand side, because now we'll have 4 oxygens from the water, and then 1 from our fatty acyl derivative. And then now we can go ahead and balance out our hydrogens. So if we count it up, we have 19 hydrogens from our fatty acyl derivative. We have 5 hydrogens from this sulfur hydryl group over here. And then we have 8 hydrogens from the water. So we add all of that up, that will give you 32 hydrogens on the right-hand side. But then we have to remember our acetyl-CoA also has hydrogens. This is a methyl group, which means it has 3 hydrogens on the end. So you actually have 3 hydrogens for every acetyl-CoA that you have. So on the left-hand side, we have 15 hydrogens from the acetyl-CoA, and then we have another hydrogen from our sulfur hydryl group. So we have a total of 16 hydrogens here. And then in order to balance this out, we'll have to add 16 hydrogens on the left-hand side to balance out the 32 that we have on the right-hand side. Okay. So now we can see if we have to balance out the charges. So over here we have 16 positive charges from the 16 hydrogens that we added, but the right-hand side is neutral. So in order to balance out the 16 hydrogens, we'll have to add 16 electrons onto this side. So now we can go ahead and do the overall net reaction. And with this, we'll just add up each thing on each side. So we can go ahead and cancel out what overlaps. So over here we have 16 electrons that we can cross out, and 16 electrons here. We also have 8 hydrogens here and then 16 on this side. So that will give you a remainder of 8 on the left-hand side. And yeah, now we can go ahead and write everything up. So you have your 8 NADPH. You have your 5 acetyl-CoA. You have your ACP sulfur hydryl group. And then you have your 8 hydrogens. And then on the right-hand side, you're going to have your 8 NADP+. You'll have your fatty acyl derivative. You'll have your CoA sulfur hydryl group. And then you have your water. So yeah, that's a general overview for how to do a redox reaction for a synthesis problem. If you're looking at an oxidation reaction, so if you were degrading like a 10-carbon fatty acid chain into 5 molecules of acetyl-CoA, the process would be really similar. You would just have different numbers and different electron donors and acceptors. But yeah.